Hello, welcome to part 2 of AP Physics C Mechanics, Newton's Laws Practice Review. So, problem 6, assuming a frictionless massless pulley, determine the acceleration of the blocks once they are released from rest. Okay, well, I'm going to say on little m, you have m1, g1. You have the tension force, which must be the same for both pulleys. So then you have the bigger block, M2G, tension force. Tension force must be the same because it's the same string. Imagine like two people pulling on two people playing tug of war, and one is smaller than the other. Doesn't matter how much force they pull on, the tension in the string will be the same. If one person pulls more, then the overall tension will be more, but the tension for each kid won't be any different. So, let's say that going around this way, then you got the pulley, it's like connected right here, blah, blah, blah. Going around this way is positive. Let's just label that, because it's going to fall this way. So assuming a frictionless massless pulley, determine the acceleration once they are released from rest. Well, let's see the acceleration so the net force on the second block is equal to m2g minus tension equals ma equals m2a. Net force on the left block is equal to well, I guess I could just use, I'm going to use big M to label the second block instead of M2. So mg, this is an M, capital M. So you got m1g. Well, actually, you have the tension because that's positive. So it'd be T minus mg equals ma. And they have the same acceleration because it's a single pulley. I believe if you have multiple pulleys, then it differs. Like one of the blocks has one half the acceleration as the other. It gets more complicated in some certain cases. But basically, the acceleration actually is the acceleration of the blocks. And so we want to solve for tension. Tension equals m times g plus a. So mg minus m times mg minus ma all over capital M is equal to acceleration. And then I want to move it over. Okay. mg plus ma. Yeah, I don't want to divide yet. So we plugged in T, so mg plus ma minus mg minus ma, distribute the negative, is equal to ma, capital Ma, Move it over, and you got mg minus capital M g minus lowercase m little block g divided by m plus lowercase m. All right, do some algebraic manipulation. You're going to move over the ma, and you're going to factor out an a. You'll get a times m plus little m. Divide m plus little m. Factor a g here, you get m minus little m times g divided by m, so e. So 7. If all forces acting on an object balance so that the net force is 0 and the object's mass remains constant. So if all forces, so there's no net force in any direction, the object must be at rest, A. It's actually not true. It could have a net force of 0 but still constant acceleration. The acceleration has to be 0. So it's not A. The object's speed will decrease, no. There's 0 acceleration. The object will follow, no, not necessarily. Actually, not at all, because that would imply acceleration. The object's direction of not necessarily, but no. The object's direction of motion can change, but not its speed. None of the above. The object's direction of motion can change. That is true. Why? Because if you have a circle, right, and the speed remains constant, the net force is 0. Or the net force, if all forces acting on an object balance. Oh, then no, because in this case, the net force, it can't be 0. Because if it was 0, then, because net force equals mv squared over r. So the net force is 0, then v would be 0. And then it wouldn't follow a circular path. So actually E is true. It's none of the above are true. An object of mass m is allowed to slide down a frictionless. Okay, that's weird. An object of mass m is allowed to slide down a frictionless ramp of angle theta. So, and its speed at the bottom is recorded as v. If the same process was followed on a planet with twice the gravitational acceleration of Earth, what would it? Well, using logic, we know that it's we can eliminate D and E. Why? Because and C actually, because we know that the velocity on this planet with twice the gravitational acceleration, it's going to be greater than on Earth, than the velocity on Earth. But we could show this. We could say frictionless ramp. I love how this thing draws. It's amazing. So you have an object, slide down a frictionless ramp. You got theta right here. So we know that the net force in the x direction will be, so this is actually normal. This is W cosine theta. This is W sine theta. So you actually have here the net force in, we'll call this x direction, down the ramp, parallel to the ramp is x, is equal to ma, but it's also equal to W sine theta. Okay, so its acceleration is equal to G sine theta. Because the weight is mg, m's cancel. So if g increases by 2, then it'll actually just be Slide down here. As seen, the speed at the bottom is v. So it's the same process with twice the gravitational acceleration on Earth. Then we know that it's. I want to use what's it called? Conservation of energy. To show that it's b, but okay. So basically, you have twice the acceleration on this planet because you're multiplying the gravity by 2. But well, it'll be so you have the weight vector and you have its components, and you know that this is, so we'll say weight on this planet is, so we know that it's twice the weight on Earth. So this is actually theta, so this is sine theta. So the accelerate, so we know that this is actually m, so 2mg sine theta is equal to a. Well, that's actually equal to the net force, but then we cancel a. So 2g sine theta. And I'm tempted to well, the acceleration's constant, so we could actually use a kinematics equation to show that, so the final velocity is equal to initial velocity is 0, some rest. So 2 times the acceleration times the x. The x is the same, so we'll say delta x, which is actually just this, is the same. So it's really just 2a, and on Earth, so it's 2a delta x. On Earth, the final velocity is 2a e delta x. Now we know that on the new planet, we'll say a sub p, the acceleration is actually 2 times the acceleration on Earth, as shown over here. Therefore, the final velocity on the new planet, sub p, is equal to the square root of 2, 4, wait, no, it's, yeah, so it's actually 2 times, so we did a substitution for, so a sub e is actually equal to, so, well, we know it would be a sub p, but that's equal, so it would be 2 times a sub p, which is equal to 2, which is equal to, so substitute, you get 2 times a on Earth, so you have a 2 right here, and you're multiplying by 2e, you get 4 a sub e is equal to delta x, and this is the same thing as, so we could do square root of 2 times square root of 2a sub e, a sub e delta x, which is v, so it's b. So you have to realize that when you, because we're used to using the kinematic equations for like just projectile motion, but they actually are valid for any situation in which the acceleration is uniform. And this is one of those cases because acceleration is only dependent upon the angle, and the angle of elevation doesn't change, nor does the gravitational acceleration. Well, technically it does change the gravitational acceleration because the distance changes, but it's so minimal that it's almost negligible. But maybe, yeah, so it's like 0.00000, you know, order of magnitude 10 to the negative n, where n is huge. N is very large, so let's see. It's negligible. An engineer is designing a loop for a roller coaster. If the loop has a radius of 25 meters, has a radius of 25 meters, okay, how fast do the cars need to be moving at the top to ensure people would be safe, even if the safety bars malfunctioned? Okay, so basically, what they're looking for is they want to know that the speed at which the cars need to be. So at the top, it's actually going to be, what's it called? Let's assume the ground is 0. So it'd actually be 50 off the ground. I want to use potential energy so much. All right, basically, so you have this, you have the weight pulling down. You have, so this is weight. And that's actually the centripetal force. So at the top, it's the net force is actually the y direction. It's equal to mv squared over r, which is equal to mg. M's cancel. You get v equals rg, the square root of rg. V is equal to so the answer is B. It's around 15.66. I guess they use G equals 10, approximately 10. So the reason for that is basically at the top, if the speed is any lower, then it's going to fall. And if the speed's any greater, then it's asking for the minimum speed. So how fast do they need to be moving? They need to be moving at least this fast. Why? Because if they're moving any slower, then basically the what's it called? They're moving any slower than the how do I phrase this? They'll basically just fall off because the weight of them will stay the same. Radius will stay the same. Well, actually, yeah, the math doesn't matter. It's the gravity. But then if their velocity is reduced, yeah, they'll just fall. I don't know how else to really put it. This is also for constant velocity, right? We need if we want the constant velocity, this is the velocity we need to be at, assuming there's no friction. All right, so I'll finish these last 3 problems in the next video. So I'll see you guys there.